Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss main memory. So, in this topic, we're going to again review or describe the purpose of main memory, and we're going to see how in main memory each byte has its own address. We will then see how these addresses are passed from the processor to main memory in parallel. This process of having a memory or an address bus is going to limit the maximum amount of memory that can be accessed by the processor. So we will describe that memory space. We will then see how main memory is used for executing programs and also see how main memory is used for the storing of a local array. Now, programs are stored in persistent memory, be that on a hard disk drive or a solid state drive. Programs are, after they are compiled, are sitting there waiting to be used. While a program is running, however, that program requires temporary memory to execute. Now, long-term memory such as hard drives can be very slow, but memory that is being accessed during execution actually has to be relatively fast. Remember that most computers today are executing at around 4 gigahertz. Main memory provides that temporary memory that can be accessed. Specifically, that memory would be accessed by the Central Processing Unit, or CPU. The CPU is what executes the instructions and contains an arithmetic logic unit as well as a floating point unit, perhaps. That CPU will be communicating with main memory. Now, to access main memory, the way that main memory is organized is that every single byte in main memory has a unique address. The CPU then sends an address to main memory and flags to either retrieve the value of the byte that is stored at that address or to set that byte to a specific value. Okay, so each byte has its own address. By the way, this is called byte addressable memory, where every single byte has its own address. The fact that every byte has its own address is not required. There are other computers where every 6 bits has its own address, and other computers where 12 bits have their own address. However, most common computers today, essentially 99.999% of them, have byte addressable memory. So every single byte has a unique address. So here we have main memory consisting of approximately 53,000 different bytes. Notice that because it is byte addressable, if you actually want to change one of these bits, you'd actually have to load the entire byte or access the entire byte and then perform bitwise and bit shift operations on that byte before you write it back into main memory. So you cannot address a bit. You can only address a byte at a time. Now, we're on the computer, and in the computer, all numbers are stored in binary. So instead of showing the addresses as decimal numbers, here we see the addresses as binary numbers. Now, how do we communicate an address to main memory to indicate which address we want? Well, suppose you had to communicate 10 digits to a friend. Well, if you were just talking to that friend, you would state each digit one at a time. This is called serial communication, sort of like a USB, a universal serial bus. Anytime you are communicating serially, you are communicating one piece of information at a time. And so therefore, if you wanted to communicate 10 digits, you'd have to specify each of those 10 digits one at a time. This, of course, can take more time. Another issue with serial communication is you have to know when you're starting a number and when you're stopping with that number. And when you get into your courses where you investigate USB and other serial communications, you will see all the various techniques that are used to deal with this. However, suppose instead you have yourself and 9 friends, and each of you communicates one of those digits to one of 10 corresponding friends. At this point, each of you only has to pass one digit to the corresponding person. And then, if each of you are speaking simultaneously, assuming you can hear over each other, you can communicate all 10 digits at once. This is described as parallel communication because each of the 10 digits is being sent over in parallel or at the same time. Serial communication is much cheaper because you only need one line. However, parallel communication is significantly faster. Well, the communication between the central processing unit, or CPU, and main memory is parallel. What we have is a bus of n lines, or wires, each of which carries one bit of an address. Now, since there's a fixed number of lines, there's a fixed number of bits that can appear in an address. So therefore, in a computer, there is a fixed number of wires or lines between the CPU and main memory that can transmit an address in parallel. Each of those n lines is sending a 0 or a 1. This means that every single address can be n bits long, and you will recall from a previous topic that if we had n bits, then we could potentially send values between 0 and 2 to the n minus 1 for a total of 2 to the n different addresses across such a bus. Now, there were many other computers before the Intel 386, but the Intel 386 was one of the first common CPUs that had a 32-bit address bus. So therefore, essentially 32 wires or lines connected the CPU and main memory to carry any address. Humorously enough, one of the first common CPUs that had a 64-bit address bus was the Nintendo 64, a gaming console. So in this setup, we had 64 wires that connected the CPU and main memory to carry any address. There is another computer you may have heard of called the Commodore 64, but it was called a Commodore 64 because it had a total of 64 kilobytes of main memory. Well, 64 kilobytes is 2 to the 16 bytes, and consequently, the Commodore 64 could have addressed all of its main memory using only 16 lines with 16-bit addresses. Alright, so if every single byte has its own address, then a 32-bit address can uniquely address 2 to the 32 or 4 gigabytes of main memory. A 64-bit address can uniquely address 2 to the 64, or approximately 67 million terabytes of main memory. Now, the reason we went from 32-bit addresses to 64-bit addresses is the restriction of having only 4 gigabytes of main memory if you had a 32-bit computer. Consequently, by the early 2000s, essentially all general-purpose computers, be they laptops, desktops, tablets, etc., had 64-bit processors. These days, you can still find 32-bit processors, and you can even find 16-bit or 24-bit addresses, but those would be mostly for embedded systems and microcontrollers. So the computers you are using are almost certainly using 64-bit addresses to access any byte in main memory. Now, if we wanted to, we could actually list all of the bytes in main memory. Every single byte has 8 bits, and every single bit would have its own unique address. So if we could list 4 gigabytes, then we could actually show each byte's address. Now that's going to get really painful really quickly if we're representing it in binary. So instead, we're going to represent addresses with hexadecimal digits. Now, if we're just writing down an address, by convention, we may leave off any leading zeros, and if we have a whole bunch of leading Fs, we may just interpolate the missing intermediate Fs with ellipsis. So, for example, instead of writing the address 0000A310, we might just write A310. And here we see how we would represent FFFFB08. And in this case, we see that it's a 32-bit system, and so it doesn't take much to figure out how many missing hexadecimal digits there are. You require, well, the number of bits divided by 4 gives you the number of hexadecimal digits you require. So a 32-bit address can be represented with 8 hexadecimal digits, and a 64-bit address can be represented with 16 hexadecimal digits. Also, if we are discussing addresses and it's rather obvious, we're probably going to leave off the leading 0x. Okay, so given this 32-bit address, we could write it as this hexadecimal number here, and I'm just showing the corresponding colors so that you can see which 4 bits corresponds to which hexadecimal digit. Similarly, if we had this hexadecimal address, then we could convert it into the 64-bit address by replacing each hexadecimal digit with its corresponding 4 bits. Thus, we could visualize all of memory as a single block of memory as shown here, and assuming that this is a 32-bit computer with a full 4 gigabytes of main memory, then the first byte would have the address 00000000, and the last byte would be represented by, in binary, all ones, or in hex as 8 Fs. Now, when a program is executed, the operating system is going to allocate some block of memory for the execution of that program. So for example, in this image here, suppose we start executing a program and the operating system allocates 256 megabytes for that execution. That's a little bit much, but here are the first and last addresses of that block of memory. We will describe the largest address as the bottom of memory and the smallest of those addresses as the top of memory for the execution of that program. Now, for the purpose of this course, we're more or less going to simply assume that each program has access to all of memory. Of course, this is not actually true, as, for example, the operating system needs some memory for itself. However, interestingly enough, we can actually maintain this facade if we use something called virtual memory. So the executing program can actually believe it has access to all 2 to the 32 bytes or 2 to the 64 bytes of potentially available memory. So in this case, the top of memory will be address 0, and the bottom of memory will be the address with all ones, which will be represented as an address of all Fs. On a 32-bit system, that would be 8 Fs. On a 64-bit system, that would be 16 Fs. Now, when you start executing a program, the instructions are loaded at the top of memory. And so this is called the code segment. You will learn more about this on your course on digital computers. But that is where the instructions will be stored and accessed from. Next, any literals or any constants will be stored in the data segment. And so if you have a string or the value of pi stored somewhere in your program, those constants will be stored in the data segment. Now, as discussed earlier, when we are executing a program, we do need memory for local variables. The memory for local variables is stored at the bottom of memory in something called the call stack. And as you need more and more local variables, the call stack is going to grow in the direction of the top of memory. We're going to discuss this in greater detail in the next topic. Now, between the end of the data segment and the start of the call stack, there's a lot of remaining additional available memory. This can be used for other features that we haven't discussed yet. So for example, local variables that keep their value between function calls, and in C++ these are called static local variables. And as well, we may have dynamically allocated memory, and that will also be allocated from this space between the data segment and the top of the call stack. Now, let's put the previous topic we discussed, which was arrays, in context with main memory. Here I have a program that has a single local variable called data. It's an array of capacity 5 storing an int. You know that an int occupies 4 bytes, and therefore 5 integers must occupy a total of 20 bytes. Suppose you execute this program and you see what the value of data is. Well, it has this particular address. I'm assuming we're running this on a 32-bit processor. However, If you were running this on a 64-bit processor, you could just add an additional 8 Fs to the left of this value. Basically, what this means is that somewhere in main memory, specifically right here, that is the address corresponding to the first byte of the 20 bytes required to store this array of capacity 5. So there are the 20 bytes, and in this 20 bytes, the first 4 bytes will be used to store the value of data 0, or the first entry of the array. The next 4 bytes will store the index 1, or the second entry of the array, and so on and so forth. Each subsequent set of 4 bytes stores the next entry. You can sort of see what happens here. If I try to access data 5, it will just now access the next 4 bytes, even though those 4 bytes are not part of this array, which can, of course, lead to problems. But if you ensure your indexing variable never goes outside the range of the array, then you shouldn't have such a problem. So this is how a local array may be stored in main memory somewhere. So following this lesson, you now know that main memory is byte addressable. That means that each byte has its own unique address. Also, you know that the processor can access any one byte in main memory by sending an address in parallel through an address bus, and that address bus has a fixed number of n lines capable of simultaneously sending n bits. You also know, therefore, that the maximum number of bytes that can be accessed is 2 to the n bytes, where n is the number of bits in any one address. Consequently, on a 32-bit address bus, the maximum amount of memory you can access is 4 gigabytes. You also know that rather than writing addresses out as bits, it's a lot easier for humans to understand them when they are written out as hexadecimal digits. And we've already covered the conversion between binary and hexadecimal in a previous topic. Consequently, you now have an idea that if you have an executing program, it is loaded from persistent memory into main memory, with the instructions being loaded into the code segment. Any constants, such as strings or floating point values, they are loaded into the data segment, and at the bottom of memory is the start of the call stack, which is used to allocate memory for local variables. You are also now aware of how an array may be stored in main memory and what the meaning of the value of a local array is if you were to print that number to the screen, that is, the address where that array begins in main memory. Here are the references, the colophon, and a disclaimer. Cheers!